let's explore 12 key points and more that will make it easier for you to understand TCP/IP transport layer function. Hello everyone and welcome. Today I aim to demystify the transport layer function by stimulating your curiosity to delve deeper into its key points. Each of these points will act as a key to unlock doors that are essential for a thorough understanding. In the next few minutes, I'll share these keys with you. So, if you're on the lookout for these insights, stick around and keep watching until the end. If you found the information helpful, please subscribe, like, and share this video and hit the notification bell. Also, please comment on which part of this video was useful for you. If you are as excited as I am, let's get started. Okay, well, what is the role of the transport layer in the TCP/IP model? The transport layer is tasked with managing end-to-end communication, ensuring the reliable and efficient delivery of data between devices on a network. In simpler terms, picture the transport layer as the traffic manager of the network, carefully orchestrating the smooth and reliable journey of data from the source to the destination. Like a skilled conductor directs the flow, ensures the packet arrives in the correct order, and corrects any errors encountered during the data transfer performance. What are the key protocols associated with the transport layer? As you know, the primary protocols at the transport layer are Transmission Control Protocol, or TCP, which provides reliable and connection-oriented communication, and User Datagram Protocol, UDP, which facilitate faster but connectionless communication. In simple terms, TCP ensures reliable and ordered communication, while UDP allows for faster data transfer without establishing a connection. How does TCP ensure reliable communication? TCP employs mechanisms such as acknowledgement, retransmission, and flow control to ensure reliable and ordered delivery of data. These features make TCP a fundamental component for secure and accurate data transmission and network communication. What is the main function of UDP? UDP provides a connectionless and faster communication method. It is often used for real-time applications where low latency is crucial, such as in streaming and online gaming. What is the significance of port numbers in the transport layer? Port numbers help identify specific applications or services on a device. They play a crucial role in the multiplexing and demultiplexing of data, ensuring that it reaches the correct application. Port numbers akin to designated doorways on a device help identify specific applications or services. Through the process of multiplexing and demultiplexing, they ensure incoming data is directed to the appropriate application, enhancing the organized and efficient flow of information in network communication. What is the concept of multiplexing in the transport layer? It's a golden question. Multiplexing involves combining multiple data streams into a single connection. The transport layer uses port numbers to multiplex different applications' data onto the same network connection. Alright, picture this. Multiplexing at the transport layer is basically like having a DJ at a party. You've got different music tracks, right? Think of those as data streams coming from various artists, which are actually different applications. Now, the magic happens when our DJ combines all these tracks into one awesome playlist. That's your network connection right there. And here's the cool part. Our DJ uses unique track number, or what we call port numbers, to seamlessly mix and deliver each song to the dance floor. And guess what? The dance floor is like our application, eagerly waiting to groove. It's all about ensuring a vibrant and organized musical experience for everyone involved. So, think of multiplexing as the DJ making sure the party rocks with each tracks hitting the right spot on the dance floor. Just like port numbers making sure data reaches the correct application. It's a networking party you won't want to miss. How does flow control work in the transport layer? Flow control mechanisms prevent fast senders from overwhelming slower receivers. TCP uses techniques like windowing to manage the flow of data and avoid congestion in the network. Let's talk about flow control in TCP. Imagine it as a traffic signal on a bustling road. Picture the sender, which is like the cars on the road, adjusting its speed according to the receiver's capacity, just like cars adapting to traffic flow. Now, if the roads start getting jam-packed due to network congestion, the sender takes a cue from the traffic signal. Kind of like TCP windowing. It's slowed down, preventing a virtual traffic jam and ensuring a smooth journey for everyone involved. It's like the dance of cars and signals creating a harmony in the network highway. Fascinating, isn't it? Can you have both TCP and UDP running on the same device simultaneously? Yes. A device can have both TCP and UDP protocols active simultaneously. Each application or service is identified by a combination of IP address and port number, allowing for multiplexing. What is the significance of the three-way handshake in TCP? The three-way handshake is a process in TCP where a connection is established between two devices. It involves SYN or synchronize, SYN-ACK or synchronize acknowledge, and ACK or acknowledge packets to ensure a reliable connection setup. After the three-way handshake, my friends, devices synchronize and initiate data transfer in a TCP connection. Data is exchanged with acknowledgements. Flow control prevents congestion, and error checking mechanisms ensure reliability, and of course the connection can be terminated gracefully when data exchange is complete. How does UDP handle errors compared to TCP? My friends, unlike TCP, UDP does not provide error checking and correction mechanisms. It is considered a connectionless protocol, which means it does not guarantee delivery, ordering, or error recovery. What is the purpose of the checksum in the transport layer? This is a very good question. Both TCP and UDP include a checksum in their headers to detect errors in the data during transmission. The checksum is used to identify potential corruption in the packet during transit. If errors are detected, the corrupted packet is discarded. You might be wondering, doesn't UDP skip error checking altogether? Okay, let me clarify. The purpose of the checksum is not to correct errors, but to identify potential corruption in the UDP packet during transit. If errors are detected, it's up to the application using UDP to decide how to handle them, since UDP does not have built-in error recovery mechanisms. For instance, voice-over IP applications or video conferencing systems that use UDP for low latency communication may choose to handle corrupted packet to ensure a smoother user experience. Okay? What is packet encapsulation and how does it occur in the transport layer? Great question. Packet encapsulation, my friends, is the process of adding headers to the original data at each layer of the networking protocol stack as it travels down from the higher layer to the lower layers. Packet encapsulation in the transport layer typically involves the addition of a transport layer header to the data received from the upper layer, typically the application layer. Okay? This process prepares the data for transmission across the network. The specifics can vary based on the transport protocol being used, commonly TCP or UDP. Let's look at them briefly. The encapsulation process in the transport layer includes multiple steps. TCP and step 1. Segmentation. The data from the upper layer application is divided into smaller units known as segments. Each segment includes a portion of the original data. Step 2. TCP header addition. A TCP header is added to each segment. The TCP header contains control information including source and destination port numbers, sequence numbers, acknowledgement numbers, control flags, and other fields necessary for reliable connection-oriented communication. Encapsulation. The original data plus the TCP header together form the TCP segment. This segment is then encapsulated into a packet suitable for transmission over the network. UDP. In UDP, we have no segmentation. Unlike TCP, UDP is a connectionless protocol that doesn't segment data into smaller units. The entire data from the upper layer application is treated as a single datagram. UDP header addition. A UDP header is added to the data. The UDP header includes source and destination port numbers, length, and a checksum for error checking. Encapsulation. The original data plus the UDP header together form the UDP datagram. This UDP datagram is then encapsulated into a packet for transmission. Now, let's look at common steps for both. Step 1. Source and destination ports. Both TCP and UDP headers include source and destination port numbers to identify the applications on the sending and receiving ends. Step 2. Checksum. UDP includes a checksum for error checking. This helps ensure the integrity of the UDP datagram during transmission. Final packet. The final packet, including the encapsulated data and the transport layer header, is then passed down to the network layer for further encapsulation. This encapsulated packet, my friends, now with both transport and network layer headers, is ready to traverse the network. The specific details of the encapsulation process may vary based on the protocols and the networking stack being used. Okay, great. With this discussion, we reached the end of this video. In the upcoming videos, we dig deeper into exciting networking world. So, if you found the information helpful, I encourage you to subscribe and hit the notification bell. This ensures you're in the loop for our future videos. Liking and sharing this video would be fantastic. It helps us reach more folks interested in these topics. And thanks a bunch for tuning in.